saw this automated hammer in Germany, and then I wanted one, and I asked them how much it cost, and they said 3,000 euros, and that was crazy. So I made my own for like $20. Still using the expensive hammer, but it's a stepper motor to control the hammer strikes, and then just some 3D printed hardware to mount it. And then also, you know, most instrument makers don't want to buy a $1,000 tiny hammer. So as Tom was mentioning, making some inexpensive ones can be quite useful. So here's my version of my inexpensive one. This is just mounted on a pendulum here. So it's all 3D printed, and it's using this tiny piezo sensor in the head of it, which has a hemispherical head on it already, which is nice, and it's actually 2 piezo sensors stacked, so you get a bit better signal to noise ratio. And then that's around $35. Maybe its price went up, maybe it's 40 now. And all the like 3D printing files and the information is on my website. And then, so next, going back to the scanning vibrometer, that is over $100,000, and I'm in a music department, so we can't afford things like that. We luckily have the single point scanning vibrometer, but not the actual commercial scanning one. So I decided to adapt mine to do scanning measurements. So going back to the force input and the measured vibrations, what we're often measuring is called the admittance, which is the ratio in the frequency domain of the resulting velocity vibrations divided by the force. So you're essentially calibrating out the force signal from that, so you know what signal you're inputting into the instrument, and you can calibrate that out. And this plot on the right is showing that. With the blue here is the frequency response of a hammer strike. So if you have a very short impulse, you'll have a flat frequency response. And then the orange is the measured velocity of the guitar vibration. This is a old Martin guitar. So you often see like a vibration mode around 100 hertz. Here you have a smaller one at 70 hertz, and then you start to get a few more around 200 hertz, and then you see these kind of patterns that repeat themselves. On violins it looks very different, but you see like a similar style of pattern. But notably this measurement, it's falling off in amplitude in the frequency response from just the velocity measurement. And that's because the hammer doesn't actually have energy there, but you can correct for it in what's called the admittance here, which is essentially boosting this energy back up to what it should actually be at. So that's kind of what we're often trying to measure when we're trying to make scientific measurements of a string instrument, and usually measured at the bridge. So here's this fancy scanning vibrometer that I can't afford. I got to use one at their company once, and it was very nice. But sad face, I don't have one, and I can't afford one. So one of the alternatives are you can use, say, either a laser or an accelerometer, and you essentially do your hammer taps at all the different locations, which can be done, but it's time consuming, and I don't want to do it because I'm lazy. So my alternative was to try to make one that can do the scans automatically. So I got this mirror. It's called a mirror galvo system. It's essentially 2 mirrors on motors that can rotate, and then you're redirecting the laser beam. And it was it was like $130. And then I made the circuits to control it, and it's all controlled with an Arduino. And it's mounted to the laser with this 3D printed attachment that holds the mirror system in front of the laser, and then it's redirecting and doing scans. And then it's excited with the same automated hammer, because you're essentially taking a measurement at each point, and then you're restriking with the hammer. Here's a video of the laser beam moving on the back of a guitar. And you can specify the grid density of how dense you want to measure. Mine, just on some quick checks, it had about a 16-degree arc. And then you can write some code to detect if there's a double hit and retake the measurement, etc. So yeah, afterwards it's doing post-processing, looking for the modes, and then getting the mode frequencies to plot. So I wanted to contrive a test case just to be able to play some audio examples. So my very contrived test case was to have a guitar with a muted back, unmuted back, and see if we could see why the mode shape is very different at the top. So I'll quickly play these so you can hear the difference. So here's okay, now that I can talk again. So that was a guitar, it's a 1947 Martin. So it's a very light guitar where my theory is that the top and back are pretty strongly coupled. And then, see here first, the unmuted version, you could hear there's a lot lower low frequency response. And then the second muted, it's the same, just like I was playing the guitar off of my chest and then against my chest, so just my chest muting the guitar. You know, two common ways you might play a guitar. And then here's an admittance measurement of, they're both struck at the bridge, that's where the strings are exciting it. And this is the admittance of the rate measured at the bridge, so the laser is pointing at the bridge right beside the hammer. And these are some of the frequencies you see in that. And then below that is still striking at the bridge, but measuring the admittance on the back. So you actually see you have these same resonant frequencies that are measured from striking on the top that are vibrating in the back very strongly as well. So if you're damping those out, you're going to damp those low frequencies, the coupling between them. And then, so here are some of the mode scans. There's still a bit of noise in the measurements, but this is, I don't know, it's something like 1,000 or 2,000 scan points. And here, obviously, this is the hammer mounting, so we can't get any measurements in front of the hammer, whereas on the back, the hammer is striking the front, the bridge location. So we see these scans. So notably, we see a couple of these modes. These two, the 100 hertz mode is actually in phase, and then the 190 hertz mode is out of phase. Yeah. And then above that, we start to see these. It's actually two on the front. It's the is it the 1-2 or the 2-1 mode, where you have this mode on the front and this mode on the back are actually roughly sharing the same frequency. So you're coupling those two modes together too. And yeah, it's nice that I can now make these scans, and it's very cheap. Here's a few more of the higher frequency modes. In the same guitar.
How fast is it?
Pretty slow. So each measurement is maybe like 5 seconds. So it depends how many you're doing. If you're doing 1,000, it's 5 seconds times 1,000.
And do you define a rectangular grid?
Yeah, I was just going over a rectangular, like a square grid, but you could define a smaller grid and speed up the time.
Okay.
I just didn't here. I set it up to send me an email if anything goes wrong, or when it's finished or when it gets to a certain amount, so I can check on it and go do something else. I'm not going to sit there for a couple hours. But this is probably overkill. Like, you don't need to take 3,000 measurements.
No, we take 150.
Yeah, if you want to take low. I just wanted to test it.
And how repeatable is
the angle?
Yeah.
Yeah, pretty repeatable.
That's nice.
Yeah, I mean, I need to do some like exact tests, but
For
I
the
haven't
price?
I haven't noticed anything wrong with it so far. So like it's probably not as good as the $100,000 laser, or that you can buy actually better galvos that are a few $1,000s that are probably better as well. But I start with the cheapest one and see how it does, and then go from there. Yeah, so that's that. Another thing I've been working on is a device to measure tone woods, to measure the material parameters, and then some other kind of get some vibration information out of it. This is a collaboration with some luthiers I work with in California at the Santa Cruz Guitar Company, and they've got a very nice stash of wood, which is great for making measurements on. So what I'm trying to measure here is have it fully automated to measure the length, width, thickness, mass, density, and then from those we're also making vibration measurements, striking with an automated hammer and recording with a sensor on the board. And then from that you can pick out the frequencies of a few of the vibrational modes and get an estimate of the stiffness along and across the grain, or the Young's modulus, and then you can get the kind of radiation coefficient. And since we're doing a hammer strike, we can get some general characterizations of kind of the frequency, equalization, and the decay of the wood. You could do a full modal fitting, but that's probably too much information for a day-to-day guitar shop, so we just broke it into like a low, mid, and high frequency bands. The logistic goals is we want it to be fast, easy, you don't have to think about it, and pretty cheap. So here's kind of one of the measurements. Strikes it, calibrates how far to go with the hammer, and then takes a few different taps where it's recording everything. And then it saves all the data to the cloud and the Google Drive, and then prints a label with all the parameters on it that you can stick on the sheet. So it's all constructed with some 80/20 general fabrication material, and then a few 3D printed parts, and then it's controlled with this microprocessor called a Teensy, which is like an Arduino, if you're familiar with that, just a little higher powered. And then it has this audio adapter as well, so you can record 2 channels of like high quality, it's 44 kilohertz 16-bit audio into it, and use it simultaneously as a serial device to control the sensors and as an audio interface. So the mass, everything's mounted on this plate, which is then mounted on a load cell to measure the mass. And then the length and width are captured with a 4K camera over top, and then some image processing, which is really overkill, but it allows adaptability up to non-rectangular boards eventually, which is kind of one of the selling points of it. And then you take a picture of it, so you have that for bookkeeping, which is nice to have. The thickness is measured with a Hall effect sensor and a magnet, similar to like a ball and something sensor, a magnet. I can't remember
the Magic Pro.
Yeah,
very similar.
yeah. It's you have a magnet on one side and this sensor on the other side, and the sensor gives a voltage that's proportional to the magnetic field strength. So if it's further apart, it will be a lower magnetic field strength. So then you can measure the thickness that way. And it doesn't have a very large range, but I was mostly focusing on guitar boards, which are pretty thin anyway, 3 to 5 millimeters for raw ones. And then the impact hammer is the same type of one, it's just a different mounting because it's 3D printed to be on this stepper motor, which controls it. And then I have another of the same piezo sensor in this clip, which sits on, and then that measures the resulting vibrations in the board. And this has an advantage over a microphone because it's a contact vibration, so you're not picking up whatever saw noise or other shop noise. You don't need a quiet room to make the measurements in. The wood is mounted on so if you think of a board, you get the 2 lowest frequency vibrations are like that, and then similarly like that. So you actually have nodes of no vibration at those 2 locations. So if you mount the board there, then you're isolating those 2 vibrations, and that's like similar. If you're trying to tap tone a board, you would hold it at that's the location you would hold it at to try to hear the lowest resonances of that board. So we're mounting the board with some foam at those two locations, and then from this, it's called the impulse excitation technique, or probably has a few other names. It's some equations that are worked out to give you an approximation of the stiffness of the board based on the frequency and then the other geometrical and mass parameters and mass of the board. And then from that, we can calculate the radiation coefficient. And it takes into account the flexural and torsional frequency, which then we can take from the vibration measurement. And then from that, we also have this vibration measurement of the whole board of, we're damping some of the frequencies because we're placing it at certain nodes, which are damping other vibrational modes, but you need to suspend the board somehow. So this is just trying to get some other information to kind of help characterize boards, like if it's a high frequency biased board or something. So I've been filtering the signal into frequency bands and then getting the signal energy. And then here in the green is showing the magnitude of the signal energy in that frequency window. And then the red is showing the decay time in the T60 decay times. It's the time for the sound to decay by 60 seconds, or 60 decibels, the time in seconds to decay by 60 decibels. You've probably heard of like the Q factor or the bandwidth, or there's like 10 different variables used for damping, and they're all related. You just need to pick one. This one's nice because it gives a number in seconds, which is kind of relatable. It's mostly used for room acoustics though. So trying to look at some of the repeatability of this. Most of the measurements are pretty good. The one thing that is the most challenging is the thickness, which is can be off by, like the uncertainty is around a few percent, which then when you're calculating the stiffness, you're doing a cube of that, which can throw it off a lot. So I thought my sensor was giving bad data, and then I found out that actually just the boards are not uniformly thicknessed, which is very frustrating. Like I could pick up a board and one side of it is at 3.9 millimeters and the other side's 4.8 millimeters. So it's not actually my sensor, it's the board. So my current fix for that is just to take more thickness measurements and do an average. Here's just a few measurements of the density on the x-axis, and here's the longitudinal stiffness in the left graph and the transverse stiffness on the right. And here, we see a variety of spruces here, with some Sitka being very stiff and then pretty dense though. So you often see a general trend of, as it is denser, it's stiffer, but that's one of the trade-offs. And then a few other interesting woods, probably not used for violins. Redwood, which is used for guitars, especially in California where redwood grows. And then sinker redwood, which is redwood that was floated down a river, sunk into the bottom of the river 130 years ago or something, and then was brought up recently. So its kind of properties are all over the place based on the minerals in the water and stuff. And like I found this board, which was like half to a third as stiff as the other ones, and it was like so flexible. If you tried to make an instrument from it, it would just break immediately, probably. So it's good to know that before you try to make an instrument from it, although with that you could probably tell by hand. And then here is just the radiation coefficient, which is similar. It's based on the stiffness and the density. Just a few examples. So currently still working on this, but it's gonna sit in this wood room probably like the week I get back to California, and then since it's very easy to use, it takes like a minute for the measurement and then uploads everything so I can get all the data, the luthiers can have the data, and then we'll start building a database and trying to do some analysis on it and then see what trends we can find. And then some future work is to do some further finite element optimization of making numerical models of the boards, and then optimizing material parameters even further with the initial guess from the measurement. And here's just a couple of the first trial runs on that, and works pretty well so far. And that's how you would also, if you're trying to do non-rectangular board objects, you'd have to do something along that lines. And I am talking way too much and going into my question time as well, I think, great, but I'll keep going for some. This is so less on the luthier measurement side, but maybe on the useful tool to study instrument side. This is some processing I've been working on to try to make an electric instrument sound like an acoustic instrument in an arbitrary way that you could then change the parameters of it and try to hear what the acoustic instrument you want to build is going to sound like before you build it, in a way that you can actually play a physical instrument and try to hear some kind of realization of what your desired acoustic instrument would sound like. So that's pretty much what I said there. So that it's based off of, it's based on the physics of the instrument, but I'd say it's inspired by the waveguide model of like physical modeling, where you have this delay line. So this represents the string. So if you have your string, you have a pulse of sound in it, say from a pluck, that travels down, it hits the bridge, and then part of the energy is transferred to the body, which is then radiated, but part of the energy is then reflected back into the string, and then it hits the nut, and then it travels back, and then you repeat that process, so when part of the energy is transmitted to the body, that's what you hear as radiated sound, but the part that's transmitted back to the string is what keeps the string ringing. So that's responsible for the sustain of the string. And with a plucked instrument, that's really important, because that interface at the bridge to the string is what governs the sustain of the instrument and the resulting sound. And Tom mentioned that the admittance that we show those graphs are, you can make a filter that is relating the admittance to the string impedance. So it's kind of an impedance scattering junction where some of the energy is transmitted through and some is reflected back. Here's kind of a bad simulation of trying to show that. So here's if you have no damping, so if you have an ideal bridge, all the energy is transmitted back to the string, and this is like what a simplified output might look like there. But if you have some number below 1, so some damping at the bridge, you'll have something that looks like this, where you start to get an exponential decay in the string, and that's what we hear is the sustain of the instrument. So what I'm trying to do is, there's been a lot of synthesis models where you're trying to mimic this interaction, and those work pretty well, but it's really hard to get the playing parameters in the synthesis. So I'm trying to take the playing parameters from an actual guitar and then mimic this interaction of the acoustic instrument, but on an electric instrument. So to do that, the string length is, and that decay time is governed by the pitch of the string. So we need to know the pitch, and then we need to know when to start it. So we need to do a transient detection, and then we need to have an admittance of the electric guitar and the acoustic guitar, and then we need to have an individual string processing on each of the string of the electric guitar. Because that filter is actually different for each string because it depends on the impedance of the string. So here's kind of the block diagram of how that's working. We have the string input. If we see a transient, we then do pitch detection, and then we reset the damping filter to account for this decay, and then we're applying this damping filter, and then we have a radiation filter after. Transient detection, there's a few ways to do it. This is one way I like. You're just tracking the level, and once you're doing an RMS energy detection and a peak detection, kind of doing like when they cross, detecting that as a transient. And then the pitch detection, there's better ways to do this. I just quickly used MATLAB's pitch function, but that's just something I need to put some more effort into doing it better of, but it works okay. Into the actual damping correction. So this is the scattering filter here, where RB is the impedance from the bridge, and RS is the impedance of the string, which is calculated as the square root of the tension times the linear mass density of the string. And then from that, we can fit our admittance to a measurement as a set of a parallel bank of resonant peaking filters. Essentially the modes, we have a frequency, a damping, and an amplitude for each of our modes. And then we can make very efficient digital filters from that. And you could fit this to a measurement, or you could have it from an arbitrary set of modes if you wanted to make it for an imaginary instrument. And then you go through and you calculate this. So this is actually the scattering filter between them, which is like a bank of parallel notch filters when you come out with the math. And then here we have that one, which is our acoustic processing one, and then we're correcting for the electric processing. I'll try to glance over the math. If anyone wants to really read it, it's in the paper, but running short on time, I want to play some sound examples. So it's iterated with it's implemented with a warped FIR filter, because it's actually an IAR filter, which is gaining two orders of every time it's implemented, which can be like 300. So I still haven't solved that problem of making a really nice IAR filter, but maybe. And then the sound radiation is just another IAR filter doing the processing here, just a different structure so we can get the phase response of the sound radiation as well. And then I just had to do some correction on the pickup I was using. So I was using an integrator on that, another filter. So into a test case of this, trying to make this electric guitar solid chunk of mahogany and maple, has almost no acoustic sound radiated, pretty much has none. The only vibrations you see in it are the neck bending, versus this old Martin, which is my guitar, so I use it a lot for measurements. Make these measurements, as I talked about before. Also used a couple microphones up with the measurements. And then here we see here's the admittance from the guitar measurement. And then in black is the measured admittance. In red is the fit admittance. So that's finding the frequency, damping, and amplitude of each of those modes. And then knowing that. And it's fit in a phase preserving way to mimic the physics and make sure if you don't match keep your phase intact, you can make an unstable filter, which we don't want. And so here's the electric guitar. You can see there's nothing below like a 800 hertz, and then we start to see a few resonances, which are the neck bending. So here's that reflection filter. So this is what the pulse at the bridge is actually seeing. So if it's a 1, it's going to reflect all the energy back, and if it's some number below, it's going to reflect less energy back. And then here's showing some of the fitting of that filtering, and then the radiation. And now finally here's some examples. So here's a clock of an acoustic guitar. Here's a clock of an electric guitar. Notice this plug here shows the T60 of the first 10 harmonics of those plugs. So that the lowest harmonic of the electric guitar plug is actually 50 seconds long, and the acoustic is 10 seconds or so. Wait, what was the first one? Oh, sorry. First one was just the pickup of the electric guitar, and this is the acoustic guitar. So much shorter pickup of the electric. Crazy one sustain, and then the process version. So that's actually an electric guitar playing, trying to mimic this acoustic guitar. It's not perfect, but it's pretty good. Here's my cat. I'll try to play some quick playing examples. So here's the hiccup. And then here's the process to sound like an acoustic guitar. Okay. It's dying, but the examples are on my website as well. And one of the fun things you can do with this is change all the response. So here's an acoustic guitar. If we shift all the modes up, it then sounds like mandolin. Yeah, anyway, I went way over time, but thank you. Questions, yeah.
It's great how when you shift on the modes,
yeah.
it sounds like a smaller guitar.
Yeah, it sounds like a smaller guitar. Yeah, so that's one of the fun things, and that's just arbitrarily shifting them.
And a cool thing I was thinking about the filters we have done, it would be nice to like program a microprocessor and put the DSP in a pedal.
Yeah.
Right?
Yeah. That's, potential future thing, maybe a product, I don't know.
Yeah, a product for us.
Yeah. That's not the focus at the moment, but it's definitely an application. Yeah. Any other questions?
Was the top wood from Santa Cruz, was that through a time saver?
No, it wasn't first. So that's one of the, we're in the discussions now if we should run everything through the time saver first before the measurements, or do like multiple thickness measurements.
Yeah.
Because I don't know, it's more work, and then you don't know what final thickness you're going to yet, and it's in the discussions of like, every time you run it through the time saver, you're taking off some of it, and then you have to glue it later, and then now you're taking off more.
Yeah. I wonder what just the variation in the thickness is from, or if there's a way of knowing, or if it's just
it's
time.
more than I would like.
Yeah, fair enough.
Yeah.
You'd probably see a similar thing if it did go through a time saver.
Oh yeah, you use just the variation in the thickness from after the time saver.
Yeah.
Probably smaller than I would guess.
Yeah, maybe. Yeah.
Like you probably wouldn't see 0.8 millimeters, right?
Yeah, fair enough. Hopefully not. You need to set up the machine again, I guess.
Yeah. All right. Well, thank you.
Cool, thanks a lot. Wanted to invite the presenters of this session. So, Henna, that's you. You guys sit here, the three of you.
Turn my video.
There's a whole chair. Pretend to sit somewhere. That's good, but we pretend to sit
I
somewhere.
want to do this later also with us, but so we have just three people.
Okay.
Just too lazy to do them myself.
Yeah. It takes a lot of time.
Yeah, no, I mean, it's the whole PMC, right?
Okay,
I feel like they're all side projects to my other things. All the tools, like it's not the focus of my PhD.
so this is a question for like both. I need to check if the camera is focus. Do I see Thomas? I don't see Thomas. No, I see Thomas. Perfect. So I hope you enjoy these talks and like what researchers are doing currently. But I would like that we think how this is gonna change, if it's gonna change, actual instrument making practice. Not now, not in 5 years, but maybe in 10 years. Like, I mean, you will have experience, you will be like 50 years old and you will like be making your instrument the same way Strat did, or are you going to include this? And what do you think it will look like? I mean, you have your own workshop, so.
I think a radiation rig would be a great place to start for acoustics measurements. I think there's already been proven out the benefits of such a system. One great website to check out in terms of how a lot of this information has been applied to violin making is the strad3d.org project. And that was a project that I think is maybe a little over 10 years old, but it was basically organized by Sam Zivkovic, a violin maker in New York, who studied 2 Strad violins and a Guarneri violin and did a very similar analysis to what I showed in my talk to those 3 violins. And then he built violins and tried to make tonal copies basically of those 3 violins. And it's interesting to see how successful he was at that and how much room for improvement there is, and how far you can go to do such a thing, to make a tonal copy. But there is evidence for how this can be useful for an instrument maker beyond just the scientific curiosities.
Do you, any of the makers, see yourself using this in the future?
Yes, definitely. I would like to kind of have instant feedback about how the acoustics of your instrument are progressing and be able to change that.
How do you select the wood now?
Good question. I mean, I personally don't know huge amounts about that. I don't know if you guys know more. But, for example, at Mondo Acustica, people take a little scale, measure, the length, and do a quick density calculation for the spruce. Also, things like, you can hold it next to your ear and gently stroke it in some kind of magical way. And, some people kind of understand from this about the quality of the wood.
And you go for some particular values of the density? Or?
Yes, I don't know what they are, but yes.
Okay.
One thing the luthiers I work with, it's a lot of tap tuning and listening, but that works if you've been doing it for 40 years and you know what to listen for, and you've made 1,000 guitars and you know what they're going to sound like based on how you hear it. But for me, that, it gives me no information to tap it and listen to it.
It's a bit like if you go and buy some wine. Like if you're very experienced, you might know about the grapes and you might have an understanding of which wines that you like. But then if you don't, it's kind of nice that there's a description that this wine might taste a little bit like fruity or a little bit sour, all that kind of thing. So it might help you to select if you don't know that much about wine. And I've been thinking why we couldn't have with the wood, for example, some kind of standardized parameters that you would always see when you're purchasing it. Why would we all have to carry our own scales and
why don't they have a label that says the density and the stiffness and the longitudinal direction or something like that?
Like some kind of tools to help you to navigate.
I mean, the selection of the companies that sell the wood is crap.
I'm not sure they know.
I don't think there's necessarily a best option either. It's whatever you want to work with. Maybe I made an instrument with these values before and I really liked it. So I want to try to make a similar instrument, or maybe I want to make something different and try something different. I don't think there's any right answer. You might work it differently if you know the stiffness. If you know the stiffness and the density are higher, then you could bring in the top thinner because it will stand up to the structural forces in that. And if you made a very dense, stiff top too thick, it probably wouldn't radiate very well. Knowing some of that.
But also you know that by then redesigning the brazing and rescalloping, you can compensate for some of the things on the top plate.
Yeah.
We know that from all the measurements from all kinds of production lines in big companies, we know that even though the top plates might have quite a big variety on the acoustic properties, then once the instrument actually like fully built, this variation shrinks to something much less. So obviously there's some. It's not just the top plate material.
I think to add to that a little bit is to stay away from the notion that there's some sort of ideal equation or numbers or density, stiffness that's like the ideal number. I think a lot of it comes from building instruments that you like how it sounds, how it turned out, or experiencing instruments where you like their tone or how they turned out, and then doing some of this analysis to maintain consistency. And as Mark was discussing with the wood measurements, if you could, you would choose wood of different material properties based on the type of guitar you're making, for example. It may be a little different for violins because there's just a lot more variation in guitar designs. But again, it's not like a ideal number or formula for this.
Yeah. I think that's one of the challenges with the measurements, because you don't really start to get a lot of useful information from it until you've done it for a little bit. Like if you take one measurement, you have nothing to compare it to, you have a single measurement. But what the value comes is when you have, 10 different measurements of different instruments and you see like, oh, this one was really different from the other ones. Why was that? Like what did I do? Do I like that or do I not like that? Like do I want to incorporate those changes or not? But yeah.
So we should force the students of looking.
No, I mean, look at it in a way, it's like science making, because you make something, you record what you did, and then on the next round you try to improve and you try to find some, relationship between how you're doing things.
Do you record? Do you keep track of? No, I mean my instruments are like, okay, this is gonna be the
but I would still like for example, the instrument maker that I work with, he notes down like at the end how did it sound like,
okay.
what kind of changes I did compared to the previous one, which kind of wood did I use, how were the properties when I did it, and then he's able to look at the logbook from years and years on to see like, okay, what has the progression been.
Yeah, Sigmuntovich also has like an amazing database. Like
Yeah.
all of his violins are
Yeah.
so and like the admittance is there. It's just like wow.
Yeah, like it's, I mean, yeah, like having something to refer to like over time to see, to get an idea also of what these tools can tell you. It's something that I don't think we can help you too much with. Like, it's just with a few measurements.
Yeah, you need more.
We probably need a standardized way of measuring to have.
Well, at least for yourself, like.
That's one thing. Yeah, and on calibration and stuff, as long as yours is consistent, then it doesn't need to be. You're probably not going and trying to publish scientific papers with the data. You just want to use it as a tool, so you don't need all of the data.
But if you want to share with other people, we will
That's the tricky part.
Yeah.
Is to have a setup in your lab where you can maintain consistency. You're probably maintaining consistent humidity if you can, and having your own measurement system that's sort of calibrated to your shop will let you take measurements for your work to compare previous instruments. It gets tricky once you want to share data and compare. I had something else I was going to say, but I can't think of it.
More questions? You are like another instrument maker here, because I noticed 3 are instrument makers. You, a student, or you or no? Visitor, what? If you want to say something, if you want to say something about yourself, okay. And you are a master's student.
Yes, we're studying acoustics.
Okay. Cool. Do you have questions?
Not really, we just started.
But do you want to like work on instruments or like sound?
That's a good question. We still have to figure out.
Okay. Yeah. Cool. Well, this is part of what we do in this area.
Well, if you want money, don't even think about it.
Hey, we don't even have coffee break.
But it's fun.
It's fun.
I will say, if you do work on instruments, talk to as many instrument makers as you can, because
Yeah.
you learn a ton from them and learn a lot about what's useful to study and what to try to focus on as well.
That's the thing, I've been thinking that if you develop all these tools for instrument makers, but then occasionally people forget that you also have to transmit the knowledge on how to use them, on like how to interpret them, on like what could they actually tell you. So it's still more beneficial to go out there and work with the instrument maker and with the acoustician together somehow. That I find that that's the best dynamic.
I think one problem we have is that we show all these bridge admittances that
Yeah.
are horrible.
Yeah.
And like we say like, yeah, you can see here like,
I was thinking about it today.
Yeah.
like, cause they, I mean, each peak corresponds to a mode, but we never show that mode, and
That's because it's so expensive to extract the
make
whole
it,
shapes.
yes.
You can like be like, oh, it's probably that low.
Yeah.
I mean, for the low frequency ones.
Yeah.
Yeah,
sure.
sure.
For example, for your 600 peak, I wanted to know what mode was.
I have no idea. That's the thing. I want to put that instrument. Nobody's ever done any model analysis on it, so that's my next goal, is to be able to understand how it actually vibrates. I mean, because the braces are so heavy, I think it's divided into many smaller regions. Like it's not like the guitar that you have. It will be working a little bit differently. But
Okay.
I would like to understand it. Yeah, but to have like an inexpensive way of running model analysis, yeah, you can try the tapping patterns, but there's still some.
Yeah, but of the whole violin, it's possible.
Yeah, exactly.
Yeah.
The whole violin control. So this is still where you still need some kind of collaboration between.
I really appreciate the science at the service of instrument making, because it's a great application for science and something that in many ways at the end is subjective. We have our preferences for instruments that we like. It sort of comes back to the art of instrument making. And to think about the archtop guitar, that the L4, that sort of style of guitar is 100 years old next year. So Gibson shipped the first L5, which was the guitar in the last slide of my presentation, 100 years ago in 2023. So we're using all this modern technology to analyze something that was refined 100 years ago. And the same is true for the violin, but a much longer time period. So it's pretty poetic, actually. It's less scientific in the end.
And you don't want to unravel the whole instrument as well.
Yeah, it's too complex.
Yeah.
We're only human. There's a limitation to
Yeah.
what we can understand. We're still evolving.
So we're also like ignoring the whole perceptual side a lot. I mean, in our talks, not that we're ignoring it, just we're not focusing on it. It's like, even for me, like looking at an admittance graph, I'm like, okay, it's an admittance graph, but like I can use it to make a filter. But what can I hear if one of those peaks is different? And how different does it have to be for me to hear it?
Yeah.
And in an actual instrument.
It's never one peak. It's sort of like everything changes.
Yeah, everything.
Yeah.
You know, you can. I played an example of when they changed by 1.5, and you
That's
can
another-
clearly hear it.
Yeah, that's.
But that's an extreme case. But like, what if they change by 1 hertz and you hear it? Is that the detail? Like, and what if they change by 2 dB? Like one mode changes by 2 dB. Can you hear that? Does that make it better? Does that make it worse? Does that make it better for one style of music and worse for another? There's so many questions.
I have a question for you, because I see that most of the studies is on model analysis, and was wondering if you, since Mark, you came here now with this perception, if you are also, if you will focus also on perceptive tests.
Yeah, I think we
at some
want
point.
to do that sometime soon.
Yeah.
Very
Now that we have the methods and stuff.
There's been some previous studies on how the mode, how the admittance and mode shapes changed by Claudia and was it Jim Wood?
Yeah, but it was all synthesis.
All
So
synthesis.
it's not.
Synthesis, sure.
It's like single plucks.
It's more controllable, probably.
Yeah, but more controllable, less realistic.
Exactly.
Yeah.
Which is always the challenging thing.
I think the idea would be to have this as another tool in the toolbox for an instrument maker.
Yeah.
I think maybe the discussion for the afternoon could be like, how are we going to do that synthesis and like virtual,
Oh yeah.
like, because I imagine, like you get the wood, you put it in your magic tester, it tells you what flavors it has, and gives you options like what kind of model you would use. And then if you could hear that,
Yeah. My ideal situation would be like, you play an instrument, you listen to it as you're playing it, and you say, oh, I don't like that one thing, I'll change that. And then you play it again, and you're like, oh, that's good, but I don't like this other thing. And you're kind of designing the instrument from the sound first.
Yeah.
And then you have to do all this like backwards problem of how do you get that sound from a pile of wood, which is a whole other challenge. We'll hear a bit more about after.
Yeah.
What do you mean by like, I don't like this?
Yeah, I mean like maybe like, okay, I like the low frequencies, but the like 800 hertz is too loud. But that's, you need to really find your fine ear. So there's other issues in how do you determine that.
You just play chords and you find one chord that doesn't sound as good as the
Yeah,
other?
maybe, or if it's just a timbral thing too, it's challenging. Yeah.
Or maybe I don't like how the notes are not like separable, so I need more separation between.
Yeah, so we know
something's like
we
this,
need
like,
less sustain, which means a higher overall admittance.
It's kind of equalizing it on guitar and
Yeah, kind of being your own audio engineer of the guitar before you play
and
it.
then just click a button and then somebody sends it to you.
Yeah, make this. Yeah, which is kind of the opposite of trying to copy other instruments.
Yeah.
Yeah. Plus, I mean, you have this problem that, the standard problem of instrument making is that a player comes to you and tells you, I want a guitar that sounds like this. But they're using words, and then from that abstract, you have to abstract, like, what kind of instrument, what kind of sound.
And everyone has different abstractions of the words.
Yeah, so it's
challenging.
Feedback?
Are we completely off, like what you guys heard?
Yeah.
That was really wonderful, thank you. That's super interesting.
Thanks for coming. I think let's go for lunch. Okay, we resume at 2. Our first
Te lascio tutti qua.